Okay, on this video, I'm starting with page 2 of the worksheet on exponential logarithmic functions. Okay, and this is really just pretty much guided notes for you. All right, and I just wanted you to have some background of what's going on, even though the focus on the homework and the test will not be graphing these things. But what's going on here, both the left and the right side, is that the base of your exponential, the base of your logarithm is a positive number bigger than 1, okay? And I just want you to have a sense of what those look like. The base might be 2 or 10 or that number e, which is about 2.72. They all have the same basic look. They all are going to do something like that. And they're going to cross right here at 1. Okay, all 3 of those. Right now, to the right of it is the logarithmic function. And these two functions are actually inverses of one another. Okay, so they have kind of a special look to them, but let me kind of show you what happens. This one is going to look something like this. Okay, it's supposed to be smoother than that. Kind of like that. Okay. And what happens is all of these that have a base understood of 10, this one really is a base of e. Those kind of functions all cross the x-axis at 1. Okay. Both of those two functions, the exponential one here and the logarithmic, they're increasing. Okay, over its entire domain. This is sometimes called a exponential growth function, where the one below it we'll find is exponential decay. So what's going on down here is we still have a positive base, still greater than 0, but it has to be less than 1. That's the other type you can have. So an example would be maybe like a base of 1/3 or 0.75. If you have a base that's positive but less than 1, rather than being growth, it's going to be decay. So it's going to do something like that. Okay. All right, and that's called exponential decay, kind of like that radioactive problem on the first page. All right, and then the logs that have a base that's less than 1 but bigger than 0, they kind of come in like so. Let's see if I can get this drawn. It's hard for me to draw this one. Something like that, okay? And that would be 1 right there. All right, so again, I'm not doing this because you're going to do much graphing, but I think it helps in the back of your mind to have a couple images to help you, okay? And an interesting relationship I want you to know is that these two functions are inverses of one another. They're inverses, kind of like squaring and square rooting, okay? They undo each other, kind of like adding 5, subtracting 5. Or if you're multiplying by 2, you would undo it by dividing. Well, exponential and logarithmic functions work the same way. So it's something kind of interesting down here. So look at the two graphs that you see above you, and you'll notice there's no x-intercept. Okay. And then also when you look at it, notice they both have the same y-intercept. 0, 1. You can just say 1. All right, now when you go look at the log side, notice that there is an x-intercept, 1, 0, which you could call just 1. People say it both ways. Okay, and the y-intercept, there isn't 1. All right, so notice how it kind of like switched. Same thing's true with what we call an asymptote. Asymptotes are kind of interesting. They're this one. Let me do it in red. The exponential functions have an asymptote initially that looks like this. This is the asymptote. Okay, both of them have the same one. You see it? It's the line, can be a curve actually, that your function gets closer and closer and closer to. Okay. Whereas over here, the asymptote is this axis. See how that is getting closer and closer and closer to the y-axis? So is this one. Okay, that's your asymptote on your log function. So on your exponential, you don't have a vertical asymptote, and you have a horizontal asymptote that's the x-axis, okay? But the x-axis means all your y's are 0. So that would be the equation of it. All right, what's going to happen over here is we do have a vertical asymptote. And the equation for it's going to be x equals 0 because it's a vertical line. And the horizontal asymptote is non-existent. So again, see how it kind of interchanged roles? That's because these are inverses of one another. All right, the domain is one thing that we actually use as we're working through problems. So you probably should pay more attention to this. The domain of an exponential, that's the x's. And see how it keeps going further and further to the left and to the right? So the domain there is all reals. But for your range, do you notice how both of them kind of approach the x-axis but don't touch it? Okay. The range is going to be from 0 to positive infinity. And that's true for both exponential there on the left. What happens for the domain on your logarithm is it's 0 to infinity. Okay. Do you remember when you got an error when you did log of 0 or natural log of -6 and you got errors when you did those? Okay. That's why. Because your graph never goes to the left of the y-axis. The range, though, on these is all reals. Okay, as you might expect from what we noticed on the other three things. Okay. All right, so the next piece on page 2 that I wanted to look at, the intent of this is really trying to get you to get a sense of what a logarithm is, okay? And so I kind of want you to remember, this is not what a logarithm is. This is just kind of related to what we're going to do. But you remember how if you had a statement, something like this, that the square root of 16 equals 4, okay, you could write that in an equivalent way by saying 4 squared equals 16 in a way. You know, they both sort of say the same thing. The thing with radicals is you understand radicals okay and you understand squares okay. So neither form is really that advantageous. You understand them both. But when you're dealing with logarithmic stuff, logs are typically very new and they're not going to make sense. And so if you can think about what it's really saying in the more familiar exponential form, you'll feel more confident about it. So that's what we're kind of getting at here. All right, so where the base is on your exponential form, that's going to be the base on the logarithm, that little subscript. And then the big idea that I want you to begin getting is that a log, the log of something, is an exponent. Okay. All right, so notice it's the exponent right here. You would need on the base, okay, in order to get y. And so log is an exponent. So it is, that's is right there. The log of something is an exponent, and the x was the exponent. So it said to put a square around the exponent in each form and put a circle around the base. Okay, we're going to use that to switch back and forth between these. So anytime I'm trying to think about what a logarithmic form means, if it's not making sense, I just switch it over to exponential form. So that's what we're practicing here, okay? All right, so first thing you're going to do is identify your base. And you know over here, that's going to be the type of log function you're dealing with. So the subscript is really attached to the log, and it's part of the name of that function. Okay, the 4 right there, that's the exponent, and that's what the log equals. So it should be on the other side of the equal sign from the log. And then the 81 is what you're going to input into the log function. Okay. So these two statements are equivalent. They both say the same thing. It's just that one's in exponential form, one's in logarithmic form. Okay. So I'm going to do a couple more of these. So here's the base. So that's going to be the base of my exponential. It's going to be raised to the -3rd power. And that should wind up being 8. They say the same thing. Okay. It's just a different way to write it. And by the way, all of these are true statements. So they really are true also. Here we're starting with exponential. We're trying to switch to log. Here's the base. That's where the base would go. Okay. The 3 is the exponent. Exponent is what the log is equal to, so that should go over there. And inside here, your input to the log function would be the 1000. And then log base 10, okay, that really means the same as just log with no number as a subscript. Those say the same thing, okay? They're both true. All right, now, if we start with this one, number 4, that one starts in log form. So we're going to take the base, and that'll be the base. This is your exponent, so that's your exponent. And then that 1 over 125 is what that should be equal to. And really, you may have forgotten this, but that negative exponent, if you remember from way back when, means to do 1 over. So it means to do 1 over 5 to the third, and 5 times 5 times 5 is 125. So you didn't need to do that, but that's why that's actually a true statement. Okay, so do you see the base here? Base is 12. So when we write our log, it's going to be base 12. Circled the wrong thing. The exponent is the 1 right here. Okay, so that's on the other side of the equal sign, and the 12 goes here. So it's saying log base 12 of 12 is 1. And I think you ought to kind of already begin playing with this. If it was log base 1/3 of 1/3, that would equal 1. If it was log base 2000 of 2000, that would equal 1. If these match, it's always going to turn out to be 1 because of this. Because 1/3 to the first power would be 1/3. And 2000 to the first power would be 2000. So these are all true because of what happens with raising something to the first power. Okay. Now this one right here is a little tricky because ln, you can't see what the base really is. So you kind of need to think about it. It really is the same as log base e of 1 equaling 0. And get used to writing these correctly. The log, the 1, the 0 should be on the same line. Okay. All right. So now we're going to think, all right, well, the base here is e. The log is the exponent. So the exponent is 0. And that statement right there really means the same as e to the 0 power equals 1. Okay. Now, ln and e are not the same thing. Okay. They're inverses of one another. So log with a base of e is the same as an exponential function with a base of e. Okay. All right. Now, this one started out in exponential form. I'm trying to put it in log form. So the base has to be 27. Okay. The exponent is 1/3. So it's going to go over here. And then this would be 3. Okay. All right. And on the last one, there's no base written. So you know it's understood to be 10. It's the common log. So the base is 10. A log is an exponent. So this is your exponent right here, -2. And we should get that to be 0.01. Okay. And the reason that's true is what's going on between here and here is 10 to the -2 means 1 over 10 squared. That means 1 over 100. And that's what that is. Okay. All right. So that's a good place to stop. That's the end of page 2. This is all stuff we did on Tuesday of last week in our live class session.